So again, we're on page 34. Everybody welcome back. I hope we had a great weekend. Here's our look at the calendar. Today is day number 2 on population growth. Last class we talked about linear growth. Today we talk about exponential growth. Next class, Fibonacci numbers in nature. Also know that the apportionment project is due today. Now this is something that you're going to email to me. Now more than half of you have emailed it already, which is great. But there are still some people that have not yet emailed it to me. So email it to me as soon as you can, as soon as it's done. If it doesn't get into me by midnight tonight, then the lateness penalties start coming in. All right, so email it as soon as it's done, and then I'll grade it and get it back to you. Alicia asked if I'm going to email them to you. I don't know. This is the first time I'm giving this project, so I haven't really thought about how I'm going to give you the feedback back, but I will. And then a week from today is Veterans Day. There are no classes, no day classes at GCC 1 week from today. Wednesday of next week is our review day. And then Monday, 2 weeks from today, is our second test. Questions on the calendar? It is not too early to start studying for that second test. You will find practice test problems in the back of the packet that you're holding right now. There are also videos on YouTube of me and or Caitlin going through those practice test problems. All right, so let's come back here. Oh, something I almost forgot. How did I almost forget this? Tomorrow, what's happening at GCC? Advising Day is tomorrow. There are no day or evening classes tomorrow, so that you guys will all have an opportunity to meet with your academic advisor and maybe register for the spring semester. A bunch of people are going to register for spring classes starting tomorrow. So go to your advisor's office door and you'll probably find a calendar of their availability for tomorrow. Sign up, make an appointment if you can come in and register. If you don't know who your advisor is, ask me right after class and I will look it up for you. In addition to the opportunity to register for next semester, there are also a whole collection of events that are happening tomorrow as well. And so we're hoping we can entice folks to come in. So for example, here we go. All right, the shortcuts that are supposed to be working aren't working. Okay, so for example, tomorrow at what is going on here? I don't understand. Okay, let's just say this. There's a PDF I can email you, and you can look at it better than I'm able to navigate through it right now. But tomorrow there are a whole collection of seminars about applying for jobs and making yourself marketable and transferring to four-year colleges. And if you want to transfer this coming spring, it's not too late. There's a whole collection of things happening tomorrow in addition to registering. So we're hoping that students don't just see it as a day to avoid GCC because there are no day classes. We want to get you guys here. So I think that this and a whole bunch of other materials have already been emailed to all of you. Check your GCC email addresses. If you want, I'm happy to email you this PDF separately, just so you can know what's going on tomorrow. Chad. Right. Cool. So maybe pick up some free stuff tomorrow. Other questions or comments? Okay, great. All right, so let's come here again on page 34. So let's go to Sana. Can you read the first part? Good. Ida, number 1. Okay, so we had 2 different kinds of growth. Linear means you add the same number every time. We looked at an example last class where we had like radioactive waste, where we were gaining like 5 tons of it every year. You guys remember? And every year was just +5 from the year before. But today we talk about something where instead of adding the same number every time, we multiply by the same number every time. And when you have that, we call it an exponential growth model. We will see very soon why the word exponential is a good word to use. You guys know exponents, like for example, here these yellow numbers are all the perfect squares, right? 6 squared is 36, 7 squared is 49. So that squared is an exponent, right? We know exponent is a power. So it's not clear that multiplying by the same amount is going to lead to a power, but we'll see it soon enough. And again, we talked about how this blue list of numbers is an exponential growth example. What do you multiply every time on the bottom row? Multiply by 2. 2 times 2048 is 4096, times 2 every time. Okay, going back to Barb for number 2. Okay, let's give this one a shot. So we start with 1,000. So I'm going to make a little table here. So this will be n, which will be the number of years. And then over here will be the number of rabbits, which we can symbolize by p sub n. So I'm going to start this one at 0, which is where we started a lot of our sequences last time. 0 again stands for initial. How many rabbits initially? 1,000. And we want to know how many rabbits at the end of our first year, at the end of 2 years, and at the end of 3 years. Okay, so let's find the number of rabbits put right here. At the end of 1 year, we know we increased by 20% per year. How much is 20% of 1,000? It's 200 plus, so we have 200 new rabbits plus the 1,000 that we already had. So we'll take the 1,000 and then we're going to add 20% of the 1,000 that we started with. So that's the 1,000 that we had plus 200 new rabbits, or 1,200 rabbits altogether. So the next row, same idea, but instead of the thousands, what number is going to be in each of those slots? Is this 1,200? So we had 1,200, and then we add 20% of 1,200. So 20% is at 240. So we had 1,200, we now gain 240. How many do we have now? 1,440. That goes in there. And if we understand that calculation, we should be able to fill in that last number. So with your table, hopefully you got a calculator handy. If not, do some arithmetic by hand, see if you can find that last number. Okay, so 1,728 at the end of that third year. Good? Okay, so here's the first question. Is this a linear growth model? Meaning, do you add the same number every time? Well, how many rabbits did we gain from 1,000 to 1,200? We gained 200. How many did we gain in the next year? We gained 240. And in the next year, 288. So linear means you gain the same amount every time. Is that the case here? No, we're not adding the same number every time, so this is not linear. But it turns out we are multiplying by the same number every time. It's 1.2. And we'll see why maybe in a second if you don't see it. But even if you don't see it, can you guys take 1,200 divided by 1,000? What do we get for 1,200 divided by 1,000? All right, so that one's easy without a calculator. That's 1.2. Okay, go ahead and do the 1,440 divided by 1,200. Which is 1.2. And then the last one, 1,728 divided by 1,440 is 1.2. So it turns out we're multiplying by the same number every time. We didn't realize that. It wasn't clear by the way I wrote the stuff in red and purple that we're just multiplying by 1.2 every time, but we are. And you can see that by doing these quotients, these divisions. Okay, so then how do we get to see that it's really just times 1.2? Well, you guys have done some factoring in your algebra days, haven't you? Do you guys buy that we can factor 1,000 out of both of those numbers? So I'm going to write that one down here. This is 1,000 factored out on the outside. how do I represent that the 1,000 that's up here in red is now completely outside? What can I put in the parentheses? Anybody know? It will become 1.2, but we're not there yet. All right, well, let's hold off on that one. I'll put the plus sign that's in the middle. If I factor 1,000 out of this term, the 1,000 goes outside. What's still there? The 0.20. So I'm going to put the 0.20 here. Let's come back to this. I'm factoring 1,000 out of this term. 1,000 goes completely outside, but we still need a placeholder to indicate we had something there before. It's a 1. And if that's not clear to you, then I would say, well, let's just distribute. 1,000 times 1 is the 1,000. 1,000 times 0.20 is exactly what we have written there, okay? So that 1 is the placeholder. Otherwise, the 1,000 would just disappear. Okay, and then this is really just 1,000 times 1.2, right? Adding up in the parentheses. And in the next one, we're not going to write it, but what could you factor out of these two? 1,200, and what would be left in this term? 1 plus what's left in this term, 0.2. And every time you factor out whatever the population was, and you're left with 1.2, which kind of makes sense because, yes, you gained 20%, but you also had the whole population that you started with last year, plus another 20%. So you had 100% of what you start with, plus another 20%. That's 120%, which is the 1.2. So then if I wanted to think about writing this as a formula in terms of n, well, let's actually not jump there. Let's go to this guy. I'm going to write down, let's see, I don't have space here. Let's squeeze it up here. Okay, I'm going to write down this. The 1728 was really 1.2 times which number? What was the previous population? 1440, right? So that's true. But that's really, 1440 was really 1.2 times what previous number? What's the 1,200? All right, all I'm doing is saying that instead of 1440, I'm writing 12 times 1.2. And then the last one, let's see, there's 1.2 there, and then 1.2 there. And then the last one, 1,200 is really 1.2 times what number? 1,000. So I'm going to write this, and then we'll check on the calculator. 1.2 times 1.2 times 1.2. I can write that in shorthand. 1.2 what? To the third power. That's what cubing a number means. And I'm going to put the 1,000 in the front just to put it in the front. So what I'd like you guys on the calculator to do is type in 1,000 times 1.2 cubed. $17.28. What's better about finding 1728 by typing in 1,000 times 1.2 cubed versus making the table? You don't have to do all the previous calculations, right? To get 1728, we needed 1440. To get 1440, we needed 1,200, and from 1,200, we needed the 1,000. But here, we just zip to the answer. So for example, if I want to know what's going on 30 years from now, couldn't you type that in very easily? Just change the 3 to a 30, and all of a sudden we have the answer without making the first 29 rows of our table. So it's some very large number, but it's something that you now have access to without the table. So here's our formula for P sub n. It's equal to the 1,000 that we started with times 1.2 raised to which power? It's n, because in the third year, it was 1.2 cubed. That 3 went up as a power. So that right there is the nifty formula for this example. Any questions so far? What's the math word for this this thing that's up here? Exponent. You guys see now why we call it an exponential growth model? Is because if you're multiplying by the same number every time, like 1.2, it naturally turns into an exponent. That's why we call it exponential growth. Okay, I think we're around to Damien for this number. Okay, so we actually did that already. We looked at the current population divided by the previous population, and we got 1.2 every time. Okay, moving on to Aileen, number 3. So we had our recursive one, which says P0 is the start amount. That's always part of the recursive. And then over here, let me just remind you what it used to be, and then I'll erase this. Used to be that if you want to know this year's population, you take last year's population, and then you just add the common difference. You guys remember that from last class? Like add 5 every time to the waste example? Well, here we're not adding 1.2 every time. We're multiplying by 1.2. So that's the formula right there. So this example for us would be to get this year, take last year and multiply by 1.20. That's the recursive formula. Okay, the explicit formula is more useful. That's right here. It says you take the start amount, multiply by the common ratio to the n. Is that what we ended up writing? So compare this to the formula you have. Started with 1,000. What is that called in the formula? Start amount. What is 1.2 called? Common ratio. N is just the right magic number to put up there. It's just n. It's whatever term you're on. Okay, so let's take a look at 4. We're now back to Kate. Okay, thank you. Can you guys with your neighbors spend a couple of minutes trying to answer all parts of this problem? Okay, so let's come back together. In the year 2045, what's the population going to be? 12 billion? I'm just going to write 12 with a B. So we double to 12 billion, and then another 45 years passes, and what do we get? We get 24 billion. And then we have a few more doublings that we're going to skip over. So did you guys like just go through the whole calculation one at a time until you got to 2450, or did you have a shortcut? What was your shortcut?
Well, I did the 24.
Mm-hmm. Okay, so how many years did you got? 360 years different here. Uh-huh. And then you divided that by 45. And you got 8. Okay. And then? So I think that means you were supposed to double 8 times, is what that means. Yeah, and that seems reasonable. The only thing, let's see, only thing I guess I would have done differently is I probably would have done from the starting year until 2450, and I would have said, okay, that's 450 years going from 2000 to 2450. And then still, we're just trying to squeeze however many 45s we can. And so I would double 10 times, but my doubling would be from 6. And you would double 8 times, starting with 24. And we'll get the same answer at the end. Chad. Yeah. And then didn't you do something to the number of years? Like you took 900 and did something to that. What did you? 900 years and divided by 45. Right. Okay. So Chad and Jeremy have proposed a formula. So we're starting with 6 billion. And we got to figure out how many times we're supposed to double. And I think you guys will agree that you take however many years have passed and you try to squeeze as many 45s into it as you can. And if you do that division, that's what you're finding is how many 45-year periods are there in your time frame. And whatever that number is, that power, well, you know, what does it mean to say, for example, 2 times 2 times 2 times 2? So it's 2 to the 4, but literally this means double, 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 double. And so that just means double 4 times. So yeah, all of a sudden it's become an exponential thing. I think that's great. Let's see, well, let me fill in the answers. What was the answer for 2450? Is that the last one or this first? 6,044 billion. Anybody else get that? Did anybody get that? Anybody get some?
Oh, yeah.
Same thing. Okay. And then the last number? This? Okay. So for example, if you wanted to get this number right here, these guys are saying you take the 900 years that have passed between 2900 and 2000, cut that into 45s. Turns out that is, what, 20. And then you raise it, use that 20 as the exponent on the number 2 because we're doubling. That 2 is the doubling part. And then in the front of that, just multiply by 6. So if you do that calculation, Chad says you'll get 6 billion and change. 6 billion billion. Okay, let's try 5. We'll go to Jake. How many years have passed between 2000 and this year? 120. Why is that number harder than the other ones that you guys dealt with? Yeah, it's not evenly divisible by 45. So 45s don't go into there evenly. If we wanted a number smaller than 120 that was nice, what number would that be? So 45 doesn't go into this one, but 90, or 45 goes into 90, right? And that's going to be too small. What's the next one that's the multiple of 45? 135? So would you guys buy that, and how many, if we take this and divide by 45, because that's going to tell us how many 45s there are, then the first number is 2 and the second number is something else, and then 3. So would you guys buy that we're going to double between 2 and 3 times? If you waited until 2090, you would double twice. If you wait all the way until 2135, you would double 3 times. Well, we're waiting something in between those. So we're going to double between 2 and 3 times. It's kind of a weird thing. I mean, how do you double a fractional number of times? Like, I know what it means to double twice and 3 times, but what does it mean to double? Somebody do this arithmetic for me here. What's the decimal when we divide? Something like that. So what does it mean to double 2.67 times? Well, I don't really know, but maybe the calculator knows. So can we try using the formula that we ended up with over here? 2 to the 2.67, and then we're going to multiply that answer by 6. What do we get? 38.19. Okay, is that answer reasonable? Let's see. You guys found the population in 2090. It was 24 billion. Is this more than that? Yeah. Yes. If we doubled one more time from here, what would we get? 48. Is that less than 48? Okay, so it's reasonable. I don't know what it means to double 2.67 times, but the calculator has some meaning it associates to it, and it gives us an answer that's at least reasonable. So that's good. So then Okay, so then let's see if we can move on to number 6 here. We'll go back to Mary. You bet. Mary, can you read 6, please? Okay, so let's answer this one here. I'm just going to write a formula to try to generalize what Chad and Jeremy came up with. I wasn't intending on writing this formula, which is why it doesn't appear already typed in the notes, but I feel like some folks are missing a piece of this and really want a formula, so I will provide that. So if you have a doubling problem, you can use this formula right here. Let's see here, Pn equals start amount times 2 raised to the n divided by the doubling time. So for example, the one that we just did, what was the start amount? 6 billion was the original population, times 2 raised to a certain power. Well, the power is whatever year you're in, divided by the doubling time, which was given in the problem, is 45 years. So if you really want a formula, there's a formula you can use for this example. Okay, so I want the yearly growth factor for the Earth's population. That is to say, I want to know by what percentage does the Earth's population go up every year. What I'm told is that it doubles in 45 years, but I want to know what it does in a single year. So I'm actually giving you the variable n. What am I saying is n for this problem? Is 1. I want to know not what's happening in 45 years or 90 years. I want to know 1 year from now. So let's try using this thing. So P1 equals 6 times 2 raised to the, what's the fraction now? As a fraction first. 1 year divided by the doubling time, which is just 45 in this whole problem. And we type this thing in, and what do we get? How much? 6 point? Give me a few more. Okay, good enough. So the population started at 6. 1 year later, it's a little bit bigger, not all that much bigger. 6.08 billion. Okay, I want to know by what percentage the Earth's population increased. How do we calculate percent growth? So that's how we convert a percentage. Anybody know how to find percent growth? I want to know what percent we went up by. We started at 6, we landed at 6.08. Anybody know how to do this? Okay, so I'll offer something here. Percent growth. I said we started at 6 and we ended at this 6.08. So what I'm really interested in knowing is what the difference is, how much we gained. So do you guys buy that that will tell me how much we gained, how many people we gained? Okay, and then I'm going to take that and divide by something. What I'm going to divide by is my starting amount. I want to compare how many people we gained relative to the original population, which was 6 billion. Somebody with a calculator type this thing in for us, please. Zero, 1, 3, 9, 5. That's a decimal. I want to know it. What's that? Yes, it's a 6, the original amount. That's a decimal. How do we convert decimals to percentages? Multiply by 100, which means decimal goes 2 places to the right. So this is really 1.395%. So that's something that I can understand a little better than doubling in 45 years. This tells me the Earth's population is growing by about 1.4% per year. That's what that says. Okay, this formula that I just used here, nobody was able to come up with that, and that's okay. It's kind of a complicated formula. There's an easier way to answer this problem. So I'm going to put this as a better alternative. Take the 2 to the 1 over 45. That was in the original problem up here. And subtract 1. Our calculator, folks, type that thing in. 2 to the 1/45 minus 1. What do we get? Did we get this? We didn't get this? What do we get? Okay, so we wrote some stuff down not quite right before. We're going to change this to 6.0931. Change this to 6.0931. And then that made this guy 0.0155, which is the same as what this guy is, 0.0155, which is 1.55%. Okay, so what do we say? If we want to find the growth factor, we do this formula right there. See it in blue right there? But instead of n, what are we saying? If we want to find the annual growth factor, what did the n become? N is 1. I just want to know what's happening 1 year from now. And so we use that formula right there. And that's the 2 to the 1/45. But if you just don't bother putting in the initial amount, subtract 1 from it, it gives you the percentage growth rates. The Earth's population growing by 1.55% per year. Okay, let's take a look at 7. Let's give this one a shot. Where are we now? Brandon, did you read? What's that? Okay, so Brandon's got this question he's read for us about having money in a bank account. I can give you $1 million today, or I can give you a penny and say that it's going to double in your account every day for the next 30 days. And I want to know which one is better. So can you guys work with your neighbors? Try to do some calculating and figure out which one will be better for you. Okay, let's look at this one. We've got our formula from Jeremy and Chad, this whole doubling business. What's the starting amount? Is 0.01 if we're thinking of it as dollars. It's okay to think of it as cents, but probably going to want to go to dollars at the end anyway. Times 2, always times 2 in a doubling problem. N is how long you have to wait. How long are we waiting? 30 days. Divided by the doubling time. In this problem, how long for stuff to double? Is 1 day. It was 45 years in the population. It's 1 day here. What is this equal to? Chad? $24. Yeah. So was it better to take the $1 million or the penny that doubles for a month? The penny. You would, and you get a little bit of interest on the 30 days, but you wouldn't get $9 million in interest, I'll tell you that. Yeah, professor in Colorado, he was like grandfather of exponential growth. Oh, great lecture. We have to look. I got to look it up. I'm interested. Okay, let's take a look at, all right, so this is the power of exponential growth. When things double, they get big very quickly. And in fact, just about any exponential growth thing you come up with gets big very quickly. The issue is that exponential growth is not all that realistic because there are resources that are finite. So like you can't have exponential growth with like a population of ladybugs because at some point you have so many ladybugs that there's not enough food to sustain them or water or there's disease and all that stuff. So we said resources are finite, but a more realistic model of growth is this logistic curve, which is a little bit more complicated. I'll say that if you watch any of the, like kind of environmental documentaries where they talk about global warming, and they end up showing a lot of very scary curves that look like this. They stop right around here. And that's the kind of thing that exponential growth does. It starts off kind of slow, but then all of a sudden we get to this kind of tipping point, and all of a sudden we're in trouble. But that's not really sustainable in a lot of places, but a logistic model is maybe more reasonable, where it does have this exponential growth behavior in the beginning, but then at some point we got to turn around and start to level off. We can't have more than like 1 billion ladybugs in our little field here at GCC. Okay, so what I want you guys to do is start on the next page and raise a flag if I can help with this bacteria activity. Okay, so let's come back together. We're jumping to the next section. Today's section was a little bit short. The next one is kind of long, so we'll push them together a little bit here. All right, I think our reader is in the back now. Griffin, not. Next page. Page 38. Okay, so you guys are going to do some more group stuff, but let's read the setup to each other and make sure we understand. Sam, female bees. Okay, so let's look at this setup because I'm going to ask you to fill in the chart. Okay, so if we take a look at one particular male bee who is alive today, and we're gonna trace this bee's family tree. We're gonna look at all the parents and grandparents and great grandparents of that one male bee. Now, surprisingly, male bees do not have two parents. Male bees have only one parent. It's always a mother. A male bee comes from an unfertilized larva. So male bees only have mothers. They have no fathers. So I'm just going to draw an arrow here, connecting that male bee to his only parent, its mom. But female bees come from fertilized larvae. So female bees have a mom and a dad. That's here and here. See it? What about this first male bee? Just a mom. There's the female. What about the female bee? There's a mother and a father. Okay, see it? True, but strange. But I want you guys to go all the way down, fill in the rest of this table,